Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to cover graphing multivariable functions using level curves today. So a level curve of z is equal to f of x comma y is defined by f of x comma y to be equal to c, where c is a constant. And really this can be thought of as taking some kind of three-dimensional function and taking some, horizontal or slices that are horizontal or perpendicular to the z-axis. So what we're going to do is we're going to take a bunch of planes and we're going to slice this thing perpendicular to this, to this z-axis. So if I take this, this bowl-looking thing, and I grab myself a plane and I slice it through this at that particular level, what we're going to see is it looks like this plane should probably slice this thing in this kind of circular shape. Now, that's not the only, slice you could take. What if we went up like a little bit higher? What if I went up here? What would happen then? So if I take, a plane at that height, well, we can see that this is going to, also be a circular shape. So far we can see that if I slice this thing this way, we can find these circular shapes, and really this is what we consider those level curves. So we can see that the pink level curve being down here would look like this. That's this level curve. And let's say that's at a height of, say, c equals 1. And then maybe this level curve, the green one, is going to be a height at maybe c is equal to 3, and we can see that this is, a bigger circle. And this might be, c is equal to 3. Should have put that in green. Which would be, this one right here. And maybe even we can do one more slice just to kind of nail this down. That what happens if we have a slice at, say this c equals 2, we also get, another circular shape at, c is equal to 2. Okay, so since this thing is bowl shaped, we can see that the circles are going to get larger as we, slice higher and higher and higher. Remember these are just z values. So z is equal to 1, z is equal to the c is equal to 1, or z. Z is equal to f of x kind of y. Z is equal to 2, and then also at z is equal to 3, we can see that we're going to get these curves. So our goal is a lot of times we can get the shape of a three-dimensional function or its graph simply by looking at its level curves as opposed to trying to hand draw something that might be pretty complicated. So let's look at a couple other ones. So I want to graph three level curves of a function. And what I want to graph is we're going to grab, three level curves, we're going to figure out some constants that I want to make this z equal to. Z is equal to 2x minus y plus 1. And sometimes the choice is obvious, and sometimes you can really pick almost anything. Now, looking at the domain of this thing with the previous video, I don't see any square roots. I don't see any divisions, any logarithms, any trig functions. So we know that the domain of this is going to be all real numbers. So if I was going to graph its domain down here, we know it would be essentially everything, all real. So negative infinity less than or equal to x less than or equal to infinity, and the same thing for the y's. So let's grab some c values. So how about like say c is equal to 0? And let's go with c is equal to, I don't know, 1, and then also c is equal to 2. And it doesn't really matter. We're just picking some c values. Since the domain is everything, when I plug anything into here, we can see that the range will also be, everything. That the range is going to, your z value is going to go from negative infinity to positive infinity. And then we'll kind of explain why this is the case when I look at its graph. Okay, so c is equal to 0. So remember, this is f of x comma y. This is z is equal to 0. We're setting, this thing equal to a constant. So 0 is equal to 2x minus, let's do this in color. Say that z is equal to, 2x minus y plus 1. We're going to do the same thing for this one, the same thing for this one. So, 1 is equal to, and then 2 is equal to 2x minus y plus 1, and similarly, this is equal to 2x minus y plus 1, just setting the z equal to these three constants. Okay, and then we're going to solve these things for something that's familiar. So we can see that they're linear, they're easy to solve, so I can send the y over to the other side, and I'll have 2x plus 1. Similarly, I can send the y over and the 1 over, so I'm going to have y is equal to just 2x. And over here, adding y to both sides and then subtracting 2 to both sides, we're going to have 2x minus 1. So when I want to look at the level curves of this thing, we can see that the level curves of this function are nothing more than, lines. So if I'm going to graph this thing, this is the xy plane, so we're really looking at its domain space when we're looking at these level curves. So 2x plus 1 would be right here. That's got a slope of 2, y-intercept of 1, so it looks something like this. We also have y is equal to 2x. Let's do this one in green. Sorry, blue. So y equals 2x would be this one. And then finally, this one will be this one in green. And we have 2x minus 1. And that's this one. And we could probably kind of guess what pattern we're getting here is, as if I go to like 3 and 4 and 5 and so on, we're just going to keep getting, you know, lines that are parallel. And if I went -1, -2, and so on, we can see these parallel lines. Now, let's kind of investigate this thing's graph real fast. I'm going to rewrite this as z is equal to 2x minus y plus 1 and see if we can get a feel for why, the level surfaces in D are supposed to look like this. So what I can see is all variables are linear, so I could send we could send the variables over to the left-hand side, so minus 2x plus y plus z is equal to 1. And we know that actually is the equation of a plane that has a normal of -2, comma 1, comma 1. So when we're looking at this, the fact that we're getting these lines is really what we have some particular plane that might look like this, that has that normal -2, 1, comma 1. And when you slice this thing, we're going to see that these slices are going to take these lines like this. So these are going to be your level curves as you move through the surface. So level curves of planes will look like lines. So it's really kind of expected that we can see that this plane is actually moving, this way. Now remember that we know the z values of these things. So um, this is drawn perfectly to scale. I'm just trying to give you an idea of what it looks like. So this is when it's 0, that has a height of z is equal to 0. This has a height of z is equal to 1, and this has a height of z is equal to uh, to 2 right here. So okay, more. All right, so the next example I want to do is f of x comma y is going to be equal to 9 minus x squared minus y squared. And I'm going to pick some c values that are going to maybe not be obvious at first, but we'll kind of see. Now, when I look at the level curves, they're not going to be as, I don't want to give it away. We'll see in a second here. Actually, let's do even c is equal to 3. Let's do an extra one just to see what happens here. Okay, so when we first let's just take a quick look at the domain, then that'll help us kind of figure out our range. So when I'm looking at the domain, I know that 9 minus x squared minus y squared has to be greater than or equal to 0 because the radicand has to be greater than or equal to 0. So that means when I add these to the other side, 9 has to be less than or equal to x squared plus y squared, or I can write the x squared plus y squared on the left-hand side, and this would be less than or equal to 9. So what I know is that the domain space of this thing is going to be, this circle of radius 3, but it needs to be less than or equal to that. So it's going to be inside here. So now I know that x squared minus y squared has to be less than or equal to 9. So this is minus, your x squared plus y squared up here. So I know that, what's underneath my hand right here, this is going to be, less than or equal to 9. So um, As long as we're good there, then I know that this is going to be 9 minus, numbers that are less than 9. So uh, the smallest this thing can be is when x and y are both 0, because if they're negative numbers squared are going to be positive. So our smallest output is going to be, again, when these things are equal to 0, which will be right here. And if those things are equal to 0, this would just be the square root of 9, which means that the biggest the z value can get is 3. And the smallest the z value can get is on this outer edge. If they're equal to 9, then 9 minus 9 will be equal to 0. The square root of 0 is 0. So I can see that the range is going to be from z is equal to 0 to z is equal to 3. So I'm actually choosing, values kind of intentionally, that this is the smallest z value you can get, this is the largest z value you can get. And we'll kind of see this shape kind of show itself over and over again. So let's kind of go through the work. All right, so when c is equal to 0, remember, we're just setting that equal to constant. So 0 is equal to this square root of 9 minus x squared minus y squared. So squaring both sides, 0 squared is equal to 9 minus x squared minus y squared. And 0 squared is 0. So adding x squared to y squared to the other side, x squared plus y squared is equal to 9. When things look circular, solve for that circle. So this is, a circle of, it's centered at, 0, comma 0 with a radius equal to 3. Similar, we're going to have f of xy is 1 is equal to the square root of 9 minus x squared minus y squared. So now squaring both sides, 1 squared is equal to 9 minus x squared minus y squared. And 1 squared is 1. So sending the 1 to the right-hand side, subtracting 1 from both sides, and then adding x squared plus y squared to both sides, we'll have x squared plus y squared is equal to 8. Now, what I was saying that it might not be the prettiest is this is still a circle, but it's got a radius of the square root of 8. So, r is going to be equal to root 8. It's still centered at 0, 0. Similar here, we have 2 is equal to the square root of 9 minus x squared minus y squared. Squaring both sides, we're going to have 4 is equal to 9 minus x squared minus y squared. So switching positions of the x squared and y squared, and then the 4, we're going to have x squared plus y squared is equal to 5. So this has a radius of root 5. And then finally over here, we have 3 is equal to that square root of 9 minus x squared minus y squared. Squaring both sides, 9 is equal to 9 minus x squared minus y squared. So x squared plus y squared on the left, subtracting 9 on both sides, we're going to get equal to 0. So that's actually a circle of radius 0. It looks like that point right here. So when I graph these, this is centered at 0 with a radius of 0, which really actually represents a point. So when I graph our level surfaces, we know the first one's circle radius 3. So that's going to give us this level surface, so circle radius 3. Remember, that has a height of 0, so that'd be at 0. Square root of 8. Jeez. 2.82. Square root of 5. 2.24. And then 0. Okay, so when we look at these radii, this one here is going to give us a level surface. This will be at a height of 1, but a radius of 2.82, so pretty close to the other one. And then this has a height of 2.24, also pretty close to the other one. This one, I'm doing my best. So just, it's 2.24, a little bigger than 2. Let's go with that. So something like this. And then finally, this one has a height of 0, which is going to look like this point right here. So these are going to be the level curves of this thing. Now I want to see if, does this make sense graphically? Well, let's investigate this function over here, just like we did similarly. So the previous example. So I know that z is equal to the square root of 9 minus x squared minus y squared. And if I square both sides, I have z squared is equal to 9 minus x squared minus y squared. Now sending the x squared and y squared to the other side, I have x squared plus y squared plus z squared is equal to 9. Now, just like um, in like your pre-calc class, when you had like y is equal to 9 minus x squared, we were talking about the top half of a circle because we were talking about the positive radical. What we have here, instead of being the top half of a circle, this right here is a sphere of radius 3. That would be a circle of radius 3 with the z squared. It's a sphere of radius 3. But again, the radical actually represents the top half of it. If I had negative here, that would be the bottom half of it. So, does this make sense? Does this look like it's going to be a sphere? Well, if you take a sphere and you slice it, this way, you're going to get, concentric circles, and they'll be pretty tight in the beginning until it like rounds off in the top, and they're going to move pretty quickly. So that's probably enough for this example. So if you like the content, please subscribe.